Here's a secret Windows Python trick you probably don't know. Microsoft has made installing Python incredibly easy on Windows. You can set it up in seconds, even if it's not installed yet. As you can see, looking at my Start menu right here, there are absolutely no traces of Python on this system. But watch what happens when we open up the terminal. Once the terminal is ready, we simply type the word Python. Even though Python isn't installed yet, watch this magic happen. When we press Enter, Windows automatically launches the Microsoft Store, and it takes us straight to the official Python page. Windows instantly recognizes the command and redirects us to the installer. All you have to do is click Get, and Windows downloads the Python Manager. Notice how seamlessly Windows detects the Python command directly inside the terminal to open the store. Once it's done, we just click Open to launch the setup. Calling this an app is a stretch since it runs right inside the terminal. So don't expect a graphical user interface. After all, this is pure Python development. Next, a standard configuration prompt pops up. It asks to bypass the 260 character limit. Should we? Absolutely. Click Yes on the user account control prompt that follows. Next, we're asked to add the installation folder directly to our environment variables. This is crucial. Select Yes. Now we confirm that we want the absolute latest Python release. Yes, we do. Within seconds, Python is completely set up and ready to go. Installation complete. Skip the online help. We don't need that. Just like that, we simply opened the terminal, typed Python, which launched the Microsoft Store. Clicked Get, then Open, and ran the setup. Just follow the simple wizard prompts. Now let's type Python in our terminal again. What happens next? Exactly. The Python interactive shell launches. Now we can execute code directly. Watch this. We're officially running Python. Let's try a quick sum. And there's our result, 10. 5 plus 5 equals 10. Windows has made installing Python incredibly simple for everyone. Welcome to your ultimate beginner's guide to Python. First, let's open the terminal on your Windows machine. Just search for terminal and launch it. Once it's open, type Python right into the command line. Press Enter to execute the command. This instantly triggers the Microsoft Store, bringing you straight to this page. Click Get to download the official Python installer. Let's wait for it to finish. It's installing now. Once complete, click Open. A new window will appear right behind the store. Go ahead and close the Microsoft Store. This is the modern way to install Python. Don't let the interface fool you. It's a clean command line interface, perfect for learning Python coding. Get ready for this. Type yes or paths exceeding 260 characters. It's a Windows rule. So type yes. When the user account control prompt appears, select yes. When asked to add commands to your path directory, hit yes. This lets you run Python seamlessly from your command line. If it notes a missing Python runtime environment and asks to install CPython now, say yes. This downloads and installs the absolute latest Python 3.14, brand new as of July 2026. Next, when prompted for online help, we will simply choose No. Awesome. Python is officially on your system. Now, let's grab your code editor. Open your browser and search for VS Code. Head straight to the official download page. You'll see options for Windows, Mac, and Linux platforms. We are going with the Windows installer today. Just give that a click. Your download will kick off automatically. Look at that speed. VS Code is downloading. Once the setup file lands, we are ready to install. Fire up the downloaded file. Accept the license agreement to proceed. Click Next. Keep the default path and breeze through the next options by hitting Next. No need to tweak a thing, just press Install. Let the wizard work its magic. Almost there. Final steps. Keep that launch checkbox ticked and click Finish. Boom, your ultimate coding playground awaits. VS Code is up and running. Skip the GitHub sign-in for now. Let's jump straight to customization. Pick your preferred look. Let's choose the sleek dark theme and hit Get Started. Close this welcome screen right here and head up to File, then Open Folder. Inside Documents, let's create a playground folder. Once created, open up that workspace. This is where your first Python file will live. First, let's establish workspace trust. Head over to Manage right here and click Trust. That clears out the security warning, giving you full access to run your code. Let's click the new file icon right inside our folder. Name it main.py. Instantly, VS Code recognizes that you need the essential Python extension. Smash that install button. This activates the core power-ups for your development workspace. Watch the progress bar right there. It'll wrap up in a second. This single pack brings incredible tools. Let's clear the extension search to see everything. Here's your clean list of active tools. It bundles everything required to run your scripts flawlessly. Let's let them finish setting up. No manual hunting needed. It automatically fetches Pylanth, the Python debugger and environments. You get the whole ecosystem in one simple installation. Forget searching for everything piece by piece. Just target Python. It intelligently triggered because of our .py file. All systems are fully green. Let's shut this tab down and head back to our project files. Open up your main.py file. Time to write your very first lines of code. Let's type out print to compute a quick calculation. 5 plus 5. Now look at the top right for that run button. Let's trigger it now. The engine executes, giving us the perfect output. The number 10 right there in the console. Just like that, you are officially a Python developer. Let's do a rapid recap. We launched the terminal and typed Python, which instantly pulled up the Microsoft Store. We grabbed the installer, deployed the runtime, and had the full environment set up in seconds. Then we searched the web for VS Code, downloaded the package, and initialized our Playground folder workspace. We added our first script and extensions. Finally, we wrote our logic and smashed run, executing it instantly right inside the editor. If you loved this guide, smash that like button and subscribe for more. Let's explore why try and except blocks are essential in Python. We start with a variable named number. We want to prompt the user to input their age. We will use the input function. This function captures whatever the user types and returns it as a string. Next, we attempt to convert that string into an integer using the int constructor. Running the script, the prompt appears in the terminal. We're asked to enter our age and press enter. Let us input the number 20. Our input is printed back, and we see 20 as an integer. But what if the user types 20 using letters instead? How will our application handle that? If we type 20 in letters, Python throws a value error. The program crashes instantly. The error message shows an invalid literal for base 10. The system simply cannot convert letters to numbers. To prevent crashes, we wrap our risky code in a tryexcept block. Inside the try block, we place the standard logic we want to run. This represents our main execution path. If something fails, we do not want the app to crash. We want a clean, controlled exit. A clean exit keeps us in control, letting us decide how to handle failures. The except clause handles a specific class of errors. Since our crash was a value error, that is the class we need. So we catch value error, and you can see it is defined as a class value error. We catch it. We add a colon and specify the block to define our fallback behavior. Instead of showing a confusing system crash, we can display a user-friendly message. Let's test this. If we input a normal number like 20, it prints age entered is 20. Now let's enter 20 using letters. It displays, please enter a whole number. The value error crash is gone. This is a much cleaner user experience. Without the except block, we would get the ugly system tracebag. So wrap your execution code inside a try block and catch errors in the except block. Let's look at handling multiple exception types. We will use Python try and except clauses. Here, we have defined an inventory. This inventory contains a keyboard and a mouse. This structure is a dictionary. We identify it as a dictionary by its key value pairs. Keys are on the left of the colon, and values are on the right, separated by commas. These are distinct items. Here is the first item, and here is the second. Think of them like records in a database. We store the product name and its stock level. Product name and stock level. Now, let's assume a user wants to query the quantity of monitors in stock. We will query our dictionary by passing the key monitor. If we retrieve the quantity, we print it. However, two things can fail here. First, the user might search for a product that is missing, like looking for monitor. Monitor is not present in our dictionary. We want to catch this key error. Show product does not exist. Second, we handle a value error. This happens if the quantity is not a valid number. We are prepared for both failures. Let us test this scenario. Running the code, the key error except block triggers, catching the missing monitor key. But if we search for a valid product, like mouse, we get the quantity 20. Now, what if the stock value for mouse is written in words? It is no longer a key error. Mouse exists, but when Python tries to convert the text to an integer, storing it in a variable to print, it crashes. This line fails when casting the string 20 to an integer. Running this, the value error is caught. It is caught cleanly. What happens if we remove the value error block? Let us see. We'll comment out these two lines and run it. We still have a tryexcept block, but guess what? Value error block is off. We get a value error crash because only key errors are being handled now. If we restore those lines and execute the code, again, we get a clean error message. You could also simplify this. You can catch errors without specifying their class type. This creates a catch-all block. Running this, the error is caught, but we are forced to use a generic message like an error has occurred, even if we remove specific handlers completely and look up monitor with just a generic except block. The handler works, but it lacks detail. For the best user experience, always catch specific errors to explain exactly what went wrong. Let's explore the try, except, and else block structure. Do you know what the else clause actually does in error handling? If not, this video is for you. We know that risky code belongs in the try block. Try except logic, but safe code should never sit inside the try block. The try section must contain only lines that might fail. Here, the risky operation is converting user input into a floating point number. If that conversion fails with a value error, we print invalid discount. If it succeeds, we want to run the else block. It confirms the discount and prints the final rate. Let's see how this behaves in practice. We will run the script. If we input a discount of 5%, it converts to a float successfully. The console displays discount accepted. Both success lines are executed. If we run it again and input 5 in letters, the value error block triggers, printing our custom error. The else block is skipped completely. You might ask, why not just put the success lines inside the try block itself? Let's try that and delete the else block. If we run this modified script and input 5, we get the same result. But here's the design problem. Print statements are safe and will never raise value errors. They are not part of the risky execution. If the conversion fails, they are bypassed anyway. Only the conversion can fail. For clean code, place your success routines. In the else block, keeping the try block minimal, limit the try block to operations that can throw exceptions. Print statements do not need protection. Many beginners clutter their try blocks with safe code that never fails. Separate the risky operations from the safe success path using the else clause. This makes your code clean and clear. Anyone reading it knows instantly which lines are expected to fail and which lines are guaranteed to run safely. Do you know what the finally clause does in Python? Let's break down how it works. Imagine you connect to a database to retrieve customer records. You start processing the data, but an error suddenly occurs. We want the except block to catch this exception. But even after showing a message to the user, we must perform some essential cleanup operations. This is where the finally block comes in. It always runs. Whether an error occurred or not, finally is guaranteed to execute. Here, we will output database connection closed. This ensures the database connection is free and we do not leak active connections. If we run this code and no errors occur, the program goes straight to the finally block and safely closes the connection. If an error occurs, the except block executes first. Immediately after, the finally block triggers, closing database connections. Let's simulate an error artificially. We will trigger a value error. This mimics a corrupt field in our customer record. Let's run this. The crash is logged in the terminal, simulating an unhandled crash. Even during a crash, the finally block still executes. We see the connection state set to close. The print statement confirms the cleanup. Use finally for resource cleanup. It guarantees that files, connections, and hardware resources are safely released every single time. How do you trigger custom errors in Python? We start with a variable named salary. We will initialize the salary to -500. A negative salary makes no logical sense. It is an invalid state. We verify this using a simple check. If salary is negative, we flag a violation. To do this, we use the raise keyword. The raise statement lets us manually trigger errors. We can choose which built-in exception class to raise. A value error fits perfectly here, since the input value is incorrect. Inside the parentheses, we can pass a custom error message string. Python will display this message when it fails. Running this code, we get a value error. The console displays, salary cannot be negative. This is a custom message instead of a generic system trace. Let's build a proper error handling block. We wrap our check in a tryexcept structure. We catch the specific value error. We store the exception object in a variable. Then we print the captured message. We also move success logic to the else block. Here is how the control flow works now. With a negative salary, value error is triggered. We catch the message. The console prints the custom error message. This is the clean way to handle custom validation rules. Let us print the message inside the except block. It extracts the error details dynamically. If we change salary to 500, the system outputs salary accepted. The entire except block is bypassed, but with -500, the success logic never executes. Previously, we triggered a custom value error exception. We set the salary variable to -500. This is a business error. No employee should ever have a negative salary. Running this code, we print a formatted message. Salary cannot be negative. We raised this error manually. This is the core concept. Python does not know whether a negative value is valid for your application. So we define the rule explicitly. If negative, raise an error. If a manager inputs a negative salary, the system blocks the operation immediately. It returns a clean validation error message. The manager can then remove the negative sign, rerun the check, and approve the salary. Let's look at how the exception carries. Our custom message. How does value error know what text to display? We catch the value error exception. We assign it to a variable named error. This captures the entire exception object. Nothing is discarded. We preserve the error object for inspection. Next, we pass this variable to print. By default, print invokes the $string method on the object. This converts the object to a string. Under the hood, print calls the string method. This returns our custom error message. We access the underlying message string. The print statement displays it directly. But where is this text actually stored? The message is stored inside the args attribute. This attribute holds the constructor arguments. Let's inspect error.args. Running this code, you see that args is actually a tuple. Since it is a tuple, we can use indexing. We can use square brackets to retrieve specific arguments. We access the first item at index 0. Running this returns the exact same string, but without the tuple formatting. It is a plain string message. This allows you to pass multiple messages. Let's add a second string argument. Now, the first error message is still returned. At index 1, we retrieve the secondary recovery message. This is how you handle multiple messages. You can print the main error first, and then display the recovery steps. This explains exactly how to fix the issue. If you print the raw error object without indexing as a tuple, like this, what happens if we print the error object directly? Will it print the first message, or will it print both? Let's test this after clearing the helper line. Running the script, both messages are output. The string conversion method retains everything inside args. It prints them as a formatted tuple. You can access each item individually. This lets you customize the output style. Now you know how custom messages are passed to built-in exceptions, stored in the args tuple, and accessed using the $string method. This gives you deep control over Python exceptions. Use these techniques to make your code robust. Next time you see this syntax, you will know exactly how it works. If this was helpful, please like, subscribe, and follow. In Python, you sometimes need to intercept an exception. Here, 25 divided by 0 causes a division by 0 error. We want to capture the exception, write it to the log, and then let the application terminate. Let's see how to do this. Inside the try block, we perform the division by 0, then trigger the catch block. The error details are recorded by the logger. Then we raise the exception again, ending execution. We get a 0 division error. The raise keyword raises the active exception. Alternatively, you could try to rethrow it by raising the error variable explicitly. But this duplicates the exception context in the traceback. It reports that another exception occurred during handling. This clutters the stack trace. Instead, use a bare raise statement to pass it along. This produces a clean single trace. It logs the error and propagates it naturally. This captures details even if you let the program crash. It helps with debugging later. What if you raise a completely different error instead? For example, let's raise a value error and inspect the resulting output. The traceback becomes quite confusing. We see the initial 0 division error, but the final error shows a failed calculation. This breaks the original error traceback. To preserve debugging details, chain your exceptions. By using raise from, you link them together. Without it, the value error hides the cause. The value error becomes the primary crash reason, obscuring the division by 0. This highlights the difference between a bare raise and raising a new exception class. A bare raise keeps the source trace clear. We see the error occurred on the division line. It is flagged as the root cause, whereas raising a new error masks the original failure.